In this video, we want to learn many different things about polynomial functions. We want to learn what is a polynomial function, what is long division of two polynomials. We will learn about synthetic division. We will learn about factor theorem and remainder theorem. We will learn how to factor polynomial functions. We will learn how to graph polynomial functions, and also we are going to learn how to find equation of a polynomial function from the given graph. So let us start with what is a polynomial function. Look at this given example, these functions here. Some of them are polynomial, some of them are not a polynomial function. For example, this first example here is a polynomial function. But what is a polynomial function? When we have x with different positive powers, like this one, which the powers are integers, so the power should be positive and not rational or decimal or radical, anything. The power should be numbers like 1, 2, 3, 4, and so on. Then it's a polynomial function. And in an equation of a polynomial function, we can have a constant number, like 7 here. Or in this equation, which is also a polynomial function, we have a 10 at the end. So these are examples of a polynomial function. Between these examples, this is a polynomial function. Because we have only x with positive powers, integer powers. Also, this is a polynomial function. What do you think about g of x? Is it a polynomial function or not? No, it's not a polynomial function. And the reason is that here we have x with the power of 1/2. Because radical x or square root of x is x to the 1/2. But as we said, in the equation of a polynomial function, we have to have only x with positive powers, and the powers should be integer, not a number like 1/2. So this is not a polynomial function. What about this function here? Is this a polynomial? No, it's not. Because in the equation of a polynomial function, we cannot have absolute. Here we have absolute of x, so this is not a polynomial function. What about h? In the equation of h of x, we have negative 3x to the 4, which is fine term. We have then x to the 2, which is also a term that can be in the equation of a polynomial. Then we have negative x to the 1, and at the end we have a constant. So nothing wrong is with this equation. So this is a polynomial function. So this is also a polynomial function. What about g of x here? X to the 2 can be in the equation of a polynomial, but what about x to the negative 2 or x to the 1/2? No, these terms cannot be in the equation of a polynomial. So this is not a polynomial function. So this is not a polynomial function. What about this one? This is obviously not a polynomial function because this is basically a rational function. Numerator of this expression is a polynomial, but we cannot have x in the denominator. So this is not a polynomial. This is a rational function. So between these functions here, only 3 of them are polynomial and the others are not polynomial functions. Now that we are a little familiar with polynomial functions, let me tell you some important things about polynomial functions. When we look at the equation of a polynomial function, for example, look at this equation here or this equation here. Immediately we notice that we have a term with the highest degree or with the highest power. Here we have x to the 3. Here we have x to the 4. The highest degree or the highest power basically of x in the equation of a polynomial is the degree of the polynomial. So what is the degree of h of x? This polynomial is basically of degree 3. What is the degree of this polynomial? This polynomial is of degree 4 because the highest degree of x or highest power of x that appears in the equation is 4. What about our first example here? What is the degree of this polynomial? This polynomial is of degree 2 because the highest power of x is 2. And attention, Sometimes the given equation is not in the order. For example, sometimes we see an equation like this: x minus x2 plus 3x to the 5. The degree of this polynomial is 5 because we have x to the 5 at the end. You should not think that always the first term shows the degree of the polynomial. No, maybe it's not in the order. Attention to this. The other thing that is important about a polynomial is leading coefficient. But what is leading coefficient? Leading coefficient of a polynomial plays an important role later for the polynomial. So pay attention. Leading coefficient. What is leading coefficient of a polynomial? We know that every polynomial has a term with highest degree. The coefficient of that term is leading coefficient. For example, look at this polynomial. Which term has the highest degree? Obviously this term. The coefficient of x to the 2 here is 1. So leading coefficient for this polynomial is 1. What about this polynomial? What is leading coefficient of this polynomial? For this polynomial, leading coefficient is negative 5. What about this polynomial here? Leading coefficient is negative 3. So, leading coefficients play an important role, especially in the graph of polynomials. Later, when we want to graph a polynomial, we will see that leading coefficient plays an important role in the graph of the polynomial functions. Other thing that is also important in the equation of polynomial functions is constant term. So we have to get familiar with these things. What is constant term? Constant term is a term in the polynomial that has no x in that term. So it's just a number. Here in this polynomial, the constant term is 7. In this polynomial, the constant term is 10. What about this polynomial? As we can see, at the end we don't have any constant, any number. So the constant term of this polynomial is 0, because you can consider this polynomial as negative 5x to the 3 plus 4x plus 0 basically. So the constant term in this polynomial is 0. Now that we are a little familiar with polynomial functions, let's talk about some special polynomial functions. Sometimes we say a polynomial is linear. What is a linear polynomial, or what is a linear function? A linear function is a function with degree 1. So if the degree of a polynomial is 1, instead of saying it's a polynomial, sometimes we say it's a linear function. Examples of linear functions are x, y equals x, or negative x plus 2, 3x plus 7, negative 2x plus 5. These are examples of a linear function which is a polynomial of degree 1. As you can see, we have only x with power 1. So when we have x to the 1, maximum degree of a polynomial is 1. It's a linear function basically. Another important polynomial function is a quadratic function. Quadratic functions are the functions that the degree of the polynomial is 2. So linear function, the degree is 1. In quadratic function, the degree is 2. The most famous quadratic function that probably you are familiar with is y equals x to the 2. The other examples are, for example, negative x to the 2 plus 3x, 2x to the 2 minus 4x plus 7. As you can see in all of these examples, the degree of the polynomial is 2. When the degree of a polynomial is 2, we can say it's a quadratic function. When we say quadratic function, it's a polynomial with degree 2. Another type of polynomials are cubic polynomials. Probably you can guess that it's a polynomial with degree 3. The most famous polynomial with degree 3 is y equals x to the 3. Other examples are, for example, negative x to the 3, y equals negative x to the 3, or y equals x to the 3 minus 4x plus 7, and you can mention infinite examples for cubic polynomials. What is a quartic polynomial? It's a polynomial with degree 4, like x to the 4, negative x to the 4, 2x to the 4 plus 3x to the 2 minus 7x plus 10. This is another example. And you can mention several examples for yourself. What is a quintic polynomial? It's a polynomial with degree 5, like x to the 5, negative x to the 5, x to the 5 minus x to the 4 plus 2x to the 3. And you can mention other examples. What is a sextic polynomial? Probably you can guess that it's a polynomial with degree 6. So that's the reason maybe they say sextic polynomial to this polynomial. X to the 6, or y equals x to the 6, negative x to the 6. And you can mention other examples for yourself. Should we memorize all of these names? Not really. Usually, if you remember only these 3, it should be enough for most cases for you. Linear function, quadratic function, and cubic functions. Cubic is degree 3, quadratic is degree 2, linear is degree 1. Of course, it's not a bad idea to learn all of this, but it's up to you. Let's move to the next important topic, long division. Long division is about how we can divide two polynomials by each other. To learn long division, the best way for learning this is doing examples. Let us start this example. Divide this given polynomial, which is of degree 3, by x plus 3. So, as a practice, this is a cubic polynomial. What is this? This is a linear polynomial, because this is degree 1 and this is degree 3. Now we want to divide that given polynomial, which is of degree 3, by this given polynomial, which is of degree 1. For dividing a polynomial by another polynomial with the long division method, the process is this. We write the dividend. The polynomial that we want to divide it is the dividend. We say dividend. And the polynomial that we divide this to that is the divisor. The divisor is x plus 3. So let me write down this for you here. So basically this is divisor, and this polynomial is dividend. So this polynomial is dividend. So it's good to learn these names. So this is dividend, this is divisor. When you want to do the long division, the process is this. Divide, then multiply, then subtract. But how? To divide a polynomial by another polynomial, you start from the highest degree of this polynomial, dividend, and you divide it by the highest degree of divisor. X to the 3, divide, as I said here, divide x to the 3 by x. If we divide x to the 3 by x, it would be x to the 2. X to the 3 divided by x is x to the 2. And you put the answer, you have to put the answer on top of the dividend. So this is the way that we write this process. So we divide the highest degree to highest degree, and we have to put the answer in here. X to the 3 divided by x is x to the 2. Then multiply. Look at the process. Divide, then multiply, then subtract. So multiply x to the 2 by the divisor. Multiply x to the 2 by x plus 3. If you multiply x to the 2 by x plus 3, it would be x to the 3, x2 times x is x to the 3 plus 3x to the 2. So you have to multiply this by all the terms in the division. Then subtract. So then you have to subtract this from this. So because we want to subtract, we put a negative outside of this. X to the 3 minus x to the 3 would be 0, and we don't need to write 0. Then we have 2x to the 2. Pay attention, we have 2x to the 2 minus 3x to the 2. So we subtract this second polynomial from this. X to the 3 minus x to the 3 is 0. 2x to the 2 minus 3x to the 2 is negative x to the 2. 2x to the 2 minus 3x to the 2 would be negative x to the 2. Then we have minus x, and because we don't have any corresponding term here, just we have to put negative x here, and then 10, we have to put 10 here. After subtraction, start again from the beginning. Divide. We have to divide this again by that. Negative x to the 2 divided by x is negative x. Now is the time to multiply. So now multiply negative x in the division. Multiply negative x by x plus 3. Negative x times x is negative x to the 2. Negative x times 3 is negative 3x. So we divided, we multiplied. Now is the time to subtract. Don't forget that you have to subtract, so you have to put a negative outside. Now please attention, this is a common mistake that happens here. If you forget this negative, you are going to get a wrong answer here as the remainder, and all the answer after this would be wrong. So please pay attention. We have a negative x2 minus negative x2. This minus is for every term here. So negative x2 basically plus x2, because minus times minus is plus. Minus x2 plus x2 would be 0. Always, please pay attention, always this with this first term should cancel and it should be 0. If it was not 0, it means that you made a mistake somewhere. Minus x2 plus x2 would be 0. Then we have minus x plus 3x. This minus multiplies by this. Minus x plus 3x is 2x. And because for 10 we don't have any corresponding term, we leave 10 here. Back to our process. Divide, multiply, subtract. We subtracted, now back to the beginning. Divide again. Now we divide again 2x by x. 2x divide by x, 2x divide by x. X with x cancels, we get 2. Now we have to do multiplication, multiply. Multiply 2 in the x plus 3, in the divisor. 2 times x is 2x. 2 times 3 is 6. Subtract again. 2x minus 2x would be 0. As usual, it should be 0. 10 minus 6 is 4. So remainder at the end is just 4. When we have to stop this process, because we know that we have to divide, then multiply, then subtract, back to the beginning, divide, multiply, subtract, divide, multiply, subtract, and so on. When we stop, when the degree of remainder, please pay attention, when the degree of the remainder is less than the divisor, we have to stop, because we cannot basically continue. Now here we don't have any more x to divide by x, so of course we cannot continue. Attention, when we get just a number as the answer of the remainder, a number is basically a constant term. A constant term can be considered always as a term with degree 0. And when remainder, the degree of remainder is less than the degree of divisor, the remainder degree is 0. The divisor degree is 1. When remainder degree is less than the divisor, we have to stop. But why a constant term can be considered as degree 0? Let me tell you the reason behind that. When we have 4, it's good to learn this. You can always consider 4 as 4 times x to the 0. Because any variable to the 0 is 1. Except 0 to the 0. 4 is basically can be written as 4 times x to the 0. As we can see, this term has a degree and its degree is 0. That's the reason that always we can consider a term that is just a number is a constant term, a term with degree 0. Back to our story. Now we know that when we divide this, which is dividend, to this divisor, we get this answer, which we name it quotient. And we get this remainder. These are very important things in a long division. Let me write down a number example for you for understanding this process. Suppose we have 10 apples. And we want to divide these 10 apples between, for example, 3 people. We know that if we divide 10 apples between 3 people, each person would receive how many apples? 3 apples. Because if we had 9 apples between 3 people, each person receives 3 apples. But because we have 10 apples, 1 apple remains. What we have to do with that 1 extra apple? We keep that here in the numerator. And still we have to divide this 1 apple between those 3 people. Which makes sense because we wanted to divide these 10 apples between those 3 people. So we divide 10 by 3. Each person receives 3 apples. 1 is remainder. And still this is divisor. So the 10 here plays the role of dividend. The 3 is divisor. The 3 is quotient. The result of division is 3. 1 is remainder. 1 apple remained. Remainder. What about this 3 which is in the bottom here? This 3 is same divisor. So divisor remains in the denominator again. Let me write this now for this example. I want to write a similar sentence for this question. We divided this big polynomial. We divided x to the 3. We divided x to the 3 plus 2x to the 2 minus x plus 10 by x plus 3. Yes. What was the quotient? Attention, this polynomial plays the role of apples. This plays the role of people. After dividing numerator by denominator, what we got as the quotient? x2 minus x plus 2. So we got x to the 2 minus x plus 2. This is our quotient. Remainder is 4. In this case, 4. What we have to put again in the denominator? X plus 3. The divisor that we had here, we have again to put in the denominator. Whenever we divide a polynomial by another polynomial, we get a quotient, which we can show briefly with q. We get a remainder, and this is the divisor that we had in the division. Let's do another example. Divide this polynomial x4 minus 3x to the 3 plus x to the 2 plus 5 by x to the 2 minus 2x, and at the end write the answer in the form of p, the given polynomial, over divisor x to the 2 minus 2x as quotient plus remainder over divisor again. Same process as we did in the previous question. So first we have to do the division, the long division. So we want to divide x to the 4 minus 3x to the 3 plus x to the 2 plus 5 by x to the 2 minus 2x. Long division is a long process, really, unfortunately. X to the 4 divide by x to the 2 again. We start. What was the process? Keep in your head. Divide, multiply, subtract. We divide first, then we multiply, then we subtract. x4 divide by x2. So we divide the highest term to the highest term. x4 divide by x2 would be x2. Then multiply x2 by x2 minus 2x, then you would get x4 minus 2x to the 3. Now we have to subtract. And because we want to subtract, we put a negative here. Do not forget, we want to subtract. x4 minus x4 is 0. Negative 3x to the 3. Plus, why I'm saying plus? Because we have a negative outside, a negative inside, negative times negative would be positive. Negative 3x to the 3 plus 2x to the 3 would be negative x to the 3, and we don't have corresponding term for x to the 2 and 5, so just copy them here. Start from the beginning. Divide, multiply, subtract, divide. Negative x to the 3 divided by x2 is negative x. Multiply negative x by the division. Negative x times x2 is negative x to the 3 plus, because negative x times negative 2x would be plus 2x to the 2. Subtract. When we subtract, in the top we have negative x to the 3 plus x to the 3 is 0. It should be 0. Always the first terms cancel. Then we have x to the 2 minus 2x to the 2, which would be minus x to the 2. And then we have to add 5. Can we continue division? Yes, we can, because we have x2 and x2, it's still divisible because the degree is the same. We stop when the degree of remainder is less than the degree of division, but still the degrees are the same, so we can continue. Negative x2 divided by x2 is negative 1. So we put negative 1 here. Multiply negative 1. Multiply negative 1 by this. It would be negative x2 plus 2x. Don't forget, we want to subtract. If we subtract, negative x2 plus x2 cancels as usual. It should cancel, otherwise you had a mistake in your calculation. In the top we have 5, and in the bottom we have a negative 2x. Attention, this negative here outside multiplies by this, so we have negative 2x and 5. It's better not to write it, the remainder, in the form of 5 minus 2x. Always write the terms with involving x. At the end, it's better to write the constants. So the better form to write the remainder is negative 2x plus 5. So this is our remainder. This is our quotient. This is the polynomial that we want to divide this by this. So this is the dividend and this is the divisor. So we are almost done. Just we have to write this in this form. P of x is this polynomial, basically is dividend. which is divided by divisor. The result of this division is the quotient, which is this polynomial. So let me write down this story here. So p of x, which is x4 minus 3x to the 3 plus x2 plus 5, is divided by x2 minus 2x. As the quotient, we got x to the 2 minus x minus 1. So this is minus x. And for the remainder, we got negative 2x plus 5. So plus negative 2x plus 5 all over x2 minus 2x. So we divided this by this. This is our quotient, this is our remainder. Now that we learned about long division, we want to learn another method for dividing polynomials. But attention, this method is not as general as the long division method. The long division method is much more powerful than this method that we are going to learn here. So maybe you think, if this method is not as general as that method, why we have to learn this extra method for dividing the polynomials? It's a good question. Because the synthetic division, which is a method, which is an alternative method for dividing polynomials, first of all, is faster, but the downside of this method is that it works only when you want to divide a polynomial by a binomial in the form of x minus a. So if you want to divide a polynomial only by something like x minus 4 or x plus 2 or x minus 5 or x plus 7 or x plus 1, only it works for cases like. So you cannot apply synthetic division to divide a polynomial by something like x to the 2 plus 4x or 3x plus 7. No, you cannot use it for any division. Only it works when you want to divide a polynomial by something like x minus or plus a number. Something in the form of x minus a. But because this method is faster, much faster than long division, if it is possible, we use this method. But in many cases, we cannot use this method. So in those cases, we have to use long division. And if you wonder why in general we have to divide a polynomial by another polynomial, there are many applications for dividing a polynomial by another polynomial. One of the applications is in finding slant asymptotes. Another application is in finding integral of a rational functions. Another application is sometimes in division of finding derivative of rational functions. And in those cases, we have to use division of two polynomials. Let's back to our story. Now that we know that we have a synthetic division, let's see what is synthetic division, how we can use it for dividing a polynomial by something like x minus a. Again, to learn the synthetic division, we start by an example. We want to divide this polynomial here by x minus 2. So divide this by synthetic division and write the answer as usual in that form. For synthetic division, the thing that makes the process of synthetic division is that we are not going to write these x to the 3, x to the 2 in x and so on in our process. Just we are going to use the numbers. Let me show you how this process works. Always you draw something like this. So you have to draw this. And then here you are going to put these coefficients in order from highest degree to the constant, to lowest degree. So the given polynomial should be in descending order basically, from highest degree to lowest degree. So you are going to just copy the coefficients of the terms, do not include x. So what is the first coefficient? 2. So we have to put 2 here. The next coefficient is 5. The next coefficient is -7. And at last we have -13. So this is for our dividend. From dividend, just copy the coefficients and put them always here. I have to mention something very important here. Suppose this polynomial was in the form of 2x to the 3 plus 5x to the 2 minus 13. So the x is missed here. We don't have any term with x. Then when you are going to put the coefficient here, to write coefficient here, please pay attention. You have to write it 2, 5, but we don't have any x. So immediately maybe you think you have to put -13 here. No. If you do it that way, you are not going to find the answer correctly. If a term is missed in the polynomial, you have to put a coefficient of that term. In this case, x is not in the equation of the polynomial. So basically we have 0x, so you have to put a 0 here. So 0 would be here, and then -13 still would be as the last term, as the last coefficient of number. So please don't forget, this is very important and it's very common mistake. What about the divisor? What we have to do with that x minus 2? From this only, please pay attention, this is also very important. You have to put only 2 here, not -2. Basically, when you want to divide by x minus a, always you have to set it equal to 0, then x would be a. Then you have to plug in that a here. So opposite sign of this number you have to always write here. So if you want to divide, for example, this by x plus 3, what number we have to write here? -3. Opposite sign of this number always goes here. Now that we wrote the first step of synthetic division, we wrote the coefficients of the dividend, and we put the number of the divisor in the proper places. Let's start the synthetic division process. In the first step, always you drop the first coefficient. So you have to write 2 below this line. Then we multiply this number by this. 2 times 2, 4. We write 4 here. Then we add these two numbers to each other. It would be now. At first, maybe you think it's complicated process, but when you do this process 2-3 times, you learn the synthetic division. Don't worry. So let me repeat the process from the beginning again. In the synthetic division, we write the coefficients. We put a number from this. Always the opposite sign goes here. Then the process starts this way. Drop this number, whatever it is, 2. Then multiply this number, which you drop, multiply it by basically by this number that you got from divisor. 2 times 2, 4. Add 5 to 4, 9. Multiply 9 by 2 again. So always multiply this by that. 9 times 2, 18. Write the 18 here. Add again this by this. 18 minus 7 or -7 plus 18 would be 11. Multiply 11 by 2. 11 times 2 would be 22. 22 plus -13 or -13 plus 22 would be 9. This last number would be your remainder. And these coefficients, attention, here we are going to get only some numbers. What these numbers mean? The original polynomial was of degree 3. You divided this polynomial by a polynomial of degree 1. So the quotient should be of degree 2. 1 less. The original polynomial was degree 3. You divided by a polynomial of degree 1. So quotient is of degree 2. 1 less. If it was degree 10, the quotient is of degree 9. So these numbers show your quotient, but only the coefficient of your quotient. But you know that the quotient is of degree 2, a polynomial of degree 2. So this means that the quotient is 2x to the 2 plus 9x plus 11. So the quotient is this and remainder is just 9. Let me write on this here. 2x to the 3 plus 5x to the 2 minus 7x minus 13 divided by x minus 2. As the quotient we got 2x to the 2 plus 9x plus 11. As the remainder we got only 9, and we have to divide this 9 by x minus 2. Let me show you another example of synthetic division. Here we want to divide this polynomial of degree 4 by x plus 2. Do you remember what was the name of a polynomial of degree 4? Quartic. Degree 5, quintic. Always for synthetic division, we draw something like this. We have to put the coefficient of dividend here. What is the first coefficient? 1. What is the next coefficient? 0. Attention, we don't have any x to the 3 in the middle here, so we have to put a 0 instead of that term. Then we have x to the 2 with coefficient negative 3. Then we expect to have x, but we don't have, so we put a 0 instead of that, and at the end we have a 6. And for x plus 2, what number we have to put here? Always the opposite sign of the number that appears in the division. Here we have x plus 2, so what number we have to put here? Negative 2. Exactly. Now let us start the process. We drop this 1, multiply 1 by negative 2, it would be negative 2. Add this by this, negative 2. Multiply negative 2 by negative 2, it would be 4. Add 1, 4 plus negative 3 is 1. 1 times negative 2 would be negative 2. 0 plus negative 2 would be negative 2. Negative 2 times negative 2 again would be 4. 6 plus 4 would be 10. This is quotient and this is remainder. From quotient, can you tell me what is the polynomial of dividing this by this? The original polynomial is of degree 4. We divided by x, so if it's 1 degree less, so the quotient is of degree 3. And these are the coefficients of the quotient. So the 1 would be the coefficient of x to the 3. So 1x to the 3, or just x to the 3, minus 2x to the 2, plus 1x, or simply x minus 2. This is our quotient. And if you want, as usual, you can write the result of division in this form, which in this case would be something like this. So we had x4 minus 3x to the 2 plus 6 divided by x plus 2. The result of this division is this quotient, x to the 3 minus 2x to the 2 plus x minus 2. Remainder is 10 over x plus 2. Now let's talk about the remainder theorem. If polynomial px is divided by x minus a, the remainder is pa. Let me explain the remainder theorem by an example here. Consider this polynomial x to the 3 plus x to the 2 minus 5. And suppose we want to divide this by x minus 2. If we divide this polynomial by this linear polynomial, we are going to have a remainder. And for dividing this polynomial by this polynomial, we can use synthetic division or line division. But for finding the remainder, only the remainder, not the quotient, based on the remainder theorem, you don't need to do any division. You can find the remainder simply by substituting 2 in this polynomial and calculating the value of this polynomial at 2, you can find the remainder. So, if we have a polynomial and we divide it by x minus a, only by substituting a in the polynomial, you can find the remainder. In this example, the remainder would be 2 to the 3 plus 2 to the 2 minus 5. 2 to the 3 is 8, 2 to the 2 is 4, 8 plus 4 is 12, 12 minus 5 would be 7. So if we divide this polynomial by this polynomial with the long division or synthetic division, doesn't matter which method to use, the remainder you would see that it would be 7. This is the remainder theorem. So remainder theorem gives you a way to find the remainder of the division without dividing the two polynomials. Now let's take a look at this example. Let Px, the polynomial, would be x to the 4 plus x to the 3 minus 3x to the 2 minus 2x minus 5. Find the quotient and remainder when this polynomial Px is divided by x minus 2. Because here we are asked to find the quotient and the remainder, we have no choice. We have to divide basically the polynomial by x minus 2. And for dividing, you can choose between long division and synthetic division. Because synthetic division is faster and easier, so let's do it with the synthetic division. As usual, we draw something like this. We put the coefficient in order. The coefficient of x to the 4 is 1, the coefficient of x to the 3 is 1, the coefficient of x to the 2 is negative 3, the coefficient of x is negative 2, and the constant term is negative 5. And because we want to divide it by x minus 2, what number we have to put here? Opposite sign of negative 2, which would be 2. So we have to put 2 here. Based on the synthetic division technique that we have learned, we drop 1 times 2. We multiply this by this already. 1 times 2 is 2. 1 plus 2 is 3. Again, multiply 3 by 2, 6. Negative 3 plus 6 is 3. 3 times 2, again 6. Negative 2 plus 6 would be 4. 4 times 2 would be 8. Negative 5 plus 8 would give you 3. So these numbers here would give you your quotient, coefficients of the quotient, and this 3 is remainder. So remainder of the division is 3. And the quotient, find the quotient from this coefficient. We know that because the given polynomial is of degree 4 and we divide it by x, so the quotient would be 1 degree less, so it's of degree 3. So the quotient, let me name the quotient polynomial qx, would be 1x to the 3 plus 3x to the 2 plus 3x plus 4. How we know that we have to start again from x to the 3? Because remember, the original polynomial is of degree 4, so the quotient would be 1 degree less than 4, so it would be degree 3. So the first coefficient is degree 3, then degree 2, degree 1, and constant. So this is the coefficient of degree 3, then degree 2, degree 1, and at the end the constant. And the 3 that remains here is remainder. So remainder is 3. In the second part of the question, we are asked to find the remainder using the remainder theorem. So in this way, we can confirm that our division was right, or maybe we had a mistake. So let's see, based on the remainder theorem, what remainder we are going to get. It should be 3. What was the polynomial in the question? The polynomial in the question was x to the 4 plus x to the 3, x to the 4 plus x to the 3 minus 3x to the 2 minus 2x, I think, minus 5, yes. And we want to find the remainder of dividing this by x minus 2. So we want to find remainder of dividing this polynomial by x minus 2. Because we want to find the remainder of dividing by x minus 2. What number we have to plug in the polynomial? 2. When you want to divide by x minus a, you have to plug in a in the polynomial. So for example, if you want to find the remainder by x minus 5, you have to plug in 5 in the polynomial. And if you want to find the remainder by x plus 3 dividing by x plus 3, what number you have to plug in the polynomial? Negative 3, always the opposite sign. So let's plug in 2 to see the remainder. 2 to the 4 plus 2 to the 3 minus 3 times 2 to the 2 minus 2 times 2 minus 5. 2 to the 4 is 16, 2 to the 3 is 8 minus 12 minus 4 minus 5. 16 plus 8, 24 minus 12 is 12, 12 minus 4 minus 5 would be 3. As we can see, the remainder is exactly the same. But finding only the remainder with the remainder theorem is of course the fastest way for finding the remainder. Here we have another example. Find only the remainder when we divide this by x minus 3. For finding the remainder, what number we have to plug in the given polynomial? 3. Opposite sign of this. So we plug in 3. 3 to the 3 minus 3 to the 4 plus 2 times 3 minus 5. P of 3 would be 3 to the 3 is 27. 3 to the 4 is 81. 2 times 3 is 6 minus 5. 27 minus 81 is negative 54. Negative 54 plus 6 is negative 48. Negative 48 minus 5 would be negative 53. So the remainder is negative 53 if you divide this polynomial by x minus 3. And you can confirm this by using the long division or synthetic division, but it's not really necessary. This is remainder theorem, so always for finding remainder of dividing a polynomial by x minus a, simply plug in the number with opposite sign in the polynomial and you can find simply the remainder. Before we jump to the next question, let me mention something here. This polynomial given here, the terms are not given in the descending order, and always it's better to rewrite a polynomial in the descending order or ascending order, but usually descending order is better. So whenever we see a polynomial like that, it's better to write it in the form of negative x to the 4 plus x to the 3 plus 2x minus 5. In this way, it's easier for us to figure out the degree of the polynomial, which in this case is 4, to figure out the leading coefficient, the sign of leading coefficient, and we know that the leading coefficient, the sign of leading coefficient, plays important role in graphing a polynomial. So always write the polynomial in descending order from highest degree to lowest degree. Let's move to the next question. Find the value of k if remainder is 3. So this is a little different question. We have a polynomial here, and now we know that when we have divided this by this, the remainder is 3. And we want to find what value of k makes this happen. So k is a number. 2, 3, negative 1 is a number, is a coefficient for x. What coefficient x should have such that the remainder of dividing this polynomial by this polynomial would give you remainder 3. So attention, we have remainder. Based on remainder theorem, we know that if we want to find the remainder of dividing this polynomial by x minus 2, simply we have to plug in 2 in this polynomial. So let me name this polynomial here p of x. And now I'm going to plug in 2. So it would be 2 to the 3 plus 2 to the 2 plus k times 2 minus 15. 2 to the 3 is 8. 2 to the 2 is 4 plus 2k minus 15. This is 2k. 8 plus 4 is 12. 12 minus 15 is negative 3. Now, based on remainder theorem again, the remainder of dividing this polynomial by x minus 2 is this. But we know that k is a number that makes this remainder 3. So this remainder that we got here, it should be equal to 3. So what we have to do here, we want this remainder be equal to 3 find k such that the remainder is 3. So 2k minus 3 should equal to 3. So from here 2k equals 6. Move the 3 to the other side, it would be 3 plus 3, or add 3 to the both side. So from here, by dividing both sides by 2, we have k equals 3. Look at the next example. For what value of m the polynomial negative 2x to the 3 plus mx to the 2 minus 5x plus 2 has the same remainder, when it is divided by x plus 2 and x minus 1. So please read the question carefully. We have a polynomial. When we divide this polynomial by x plus 2 and separately when we divide it by x minus 1, we have same remainder. So when we divide by x plus 2, we get a remainder. When we divide by x minus 1, we get different remainder. But these two remainder are the same based on the question. What is m? Based on remainder theorem, again we say the remainder in each case is when we divide by x plus 2, what number I have to plug in my polynomial for finding the remainder based on the remainder theorem? Negative 2. If I want to find the remainder when I divide by x minus 1, what number I have to plug in my polynomial? 1. Opposite sign of those numbers. Let's find the remainder in each case separately first. Let's plug in negative 2. Then we have negative 2 times negative 2 to the 3 plus m times negative 2 to the 2 minus 5 times negative 2 plus 2. Let's plug in 1. Then we have negative 2 times 1 to the 3 plus m times 1 to the 2 minus 5 times 1 plus 2. Negative 2 to the 3 is negative 8 times negative 2 is 16. Negative 2 to the 2 is 4 times m is 4m. Then we have 10 plus 2. This equals to 10 plus 2, 12 plus that 16 is 28. So we have 4m plus 28. This equals to negative 2 plus m minus 5 plus 2. Negative 2 and plus 2 cancel each other, so it equals m minus 5. Now, when we divide this polynomial by this is our remainder. When we divide this polynomial by this is our remainder. Now our job is to find m such that we have same remainder. So we have to figure out what value of m makes these two remainder equal to each other. So we have to set 4m plus 28 equal to m minus 5. If we move m to the other side, it would be 3m, 4m minus m, and we move 28 to the other side, negative 5 minus 28 would be negative 33. So from here, m is negative 11. And this is the solution of this question. So as you can see, remainder theorem has many applications, and we can solve several questions with the aim of remainder theorem. So remainder theorem is a critical theorem that has many applications for solving questions. Let's see what is factor theorem. X minus a is a factor of the polynomial px if and only if p of a is 0. To understand the factor theorem, let me give you an example. Consider this polynomial x to the 3 plus x to the 2 minus 5x minus 2. For example, x minus 1 is a factor of this polynomial, which means that we can factor this polynomial in the form of x minus 1 times by something if when we plug in 1 in the polynomial, if p of a, p of 1 equals to 0. So x minus 1 is a factor of this polynomial if p of 1 is 0. Otherwise, x minus 1 is not a factor of this polynomial. If we plug in 1 in this polynomial, we have this. By calculating this, it is 1 plus 1 minus 5 minus 2, and it equals negative 5. Is it equal to 0? No. And because when we plugged in 1 in this polynomial, it's not 0. So x minus 1 is not one of the factors of this polynomial. But x minus 2 is a factor of this polynomial. How we can check this? To see that x minus 2 is a factor for this polynomial or not, we have to plug in 2 in this polynomial. Then we have 2 to the 3 plus 2 to the 2 minus 5 times 2 minus 2. It equals to 8 plus 4 minus 10 minus 2. Is 12 minus 12 is 0. Because p of 2 is 0, based on the factor theorem, we know that if we factor this polynomial, one of the factors definitely is x minus 2. So, factor theorem is a useful tool for us to figure out the factors of a polynomial. So it can be helpful for factoring polynomials. Let's see this example. Which of these binomials are factors for this polynomial? Binomial means we have two terms. Look at these expressions, all of them have two terms. X minus 1, x minus 3, x plus 3. These are binomial. This is the meaning of binomial. Which of these binomials are factors of this polynomial? Based on the factor theorem, we know that x minus 1 is a factor for this polynomial if p of 1 equals 0. If we plug in 1 in this polynomial, we have 1 to the 3 minus 3 times 1 to the 2 minus 1 plus 3. 1 to the 3 is 1 minus 3 times 1 to the 3. 1 to the 2 is negative 3. So we have 1 minus 3 minus 1 plus 3. It equals to 0 clearly. So this is a factor for this polynomial. Now we want to know that is this also a factor for that polynomial or not? How we can check it based on the factor theorem? It's very simple. We plug in negative 3. Attention, x minus a is a factor if p of a, not this number, opposite sign of this number that appears here, you have to plug in the polynomial. So to check that x plus 3 is a factor or not, you have to plug in negative 3 in the polynomial. If it is 0, it's a factor. If it's not 0, it's not a factor. Negative 3 to the 3 minus 3 times negative 3 to the 2 minus negative 3 plus 3. Negative 3 to the 3 is negative 27. Negative 3 to the 2 is 9 times by negative 3 is again negative 27. Then we have plus 3 plus 3. Negative 27 minus 27 is minus 54. Plus 6 is minus 48. Because this is not 0, so this is not a factor. But this is a factor. So far we know this. Now what about this? We can check it with p of 3. If p of 3 is 0, then it is a factor. Then we have 3 to the 3 minus 3 times 3 to the 2 minus 3 plus 3. This is plus. 27 minus 27 minus 3 plus 3. It is 0. So this is also a factor for that polynomial. What about x plus 1? We can check it simply by substituting negative 1. Then we have negative 1 to the 3 minus 3 times negative 1 to the 2 minus negative 1 plus 3. It equals to negative 1 minus 3 plus 1 plus 3. It is 0. So this is also a factor. So these are the factors of this cubic polynomial. This is a polynomial of degree 3, so it's a cubic polynomial. And because it's of degree 3, if we factor it, if we can factor it fully, it should have how many factors? 3 factors at most. And exactly the factors are these expressions. So it's not part of this question, but let me tell you something here. Now we know that if we factor this polynomial fully, The answer is x minus 1 times x minus 3 times x plus 1. The order of writing these factors doesn't matter, but these are the factors, which means that if we multiply all of them by each other, attention, we have 3 factors. We have x, x, and x. If we multiply these, we are going to get x to the 3. So the factored form of that given polynomial is x minus 1 times x minus 3 times x plus 1. Now let's see what is integral 0 theorem. If x minus a is a factor for the polynomial px with integral coefficients, so attention, for not every polynomial we can use this integral 0 theorem. The polynomial should be, for example, something like this, that the coefficients of each term are integral coefficients. The coefficients should not be fractions. We should not have radical numbers as the fraction. So for example, we cannot have a 2 over 3 or 1/2 as the coefficient for our terms in our polynomial. Then a is a factor of the constant term of the polynomial. Let me explain the integral 0 theorem by doing this example together here. We want to factor this polynomial fully. To find the possible factors of this polynomial, we look at this constant term here, -6. What are the factors of 6 or -6? Plus minus 1, plus minus 2, plus minus 3, and plus minus 6. By writing the factors of 6 or -6, which are these numbers, now we know that the possible factors for this polynomial are x plus or minus 1, x plus minus 2, x plus minus 3, and x plus minus 6. But how we know which one of these is a factor actually or not? Because these are possible factors with the aim of remainder theorem, with the aim of actually factor theorem, not remainder theorem. To figure out which one of these are a factor or not, we use the factor theorem. We plug in 1 in this polynomial. If it makes, based on the factor theorem, this polynomial equal to 0 at this point, then we know that x minus 1 is a factor for this polynomial. Let's plug in 1 here. If we plug in 1, then we have 1 to the 3 plus 2 times 1 to the 2 minus 5 times 1 minus 6. 1 to the 3 is 1, 2 times 1 is 2 minus 5 minus 6. 1 plus 2 is 3, 3 minus 5 is -2, -2 minus 6 is -8. Because it's not equal to 0, so x minus 1 is not a factor for this polynomial. Then we try, of course, -1. Then we have -1 to the 3 plus 2 times -1 to the 2 minus 5 times -1 minus 6. This would be -1 plus 2 plus 5 minus 6. -1 plus 2 is 1, 1 plus 5 is 6, 6 minus 6 is 0. So, because p of -1 is 0, we know that x plus 1 is a factor for p of x. So now we know that one of the factors of this polynomial is x plus 1. Now that we have one of the factors, we use synthetic division and we divide this polynomial of degree 3 by x plus 1 to get a polynomial of degree 2. Then we are going to factor that polynomial. Because when the degree of the polynomial reduces 1 unit, factoring that polynomial would be easier. So we are not going to test the next numbers. No. Immediately after we got one of the factors, we are going to use synthetic division. After the synthetic division, we get a new polynomial and we work on the factoring that new polynomial. So let's do it. So we want to divide this polynomial x to the 3 plus 2x to the 2 minus 5x minus 6 by x plus 1 with the synthetic division. Or you can use long division, but I prefer to use synthetic division because it's faster, as you know. We are going to use the coefficient 1, 2, -5, -6. What number we have to put here? The opposite sign of x plus 1, which is -1. Actually, this number which was here. Based on the synthetic division, we drop this 1. It goes here. 1 times -1 is -1. 2 plus -1 is 1. 1 times -1 is again -1. -5 minus plus -1 would be -6. -6 times -1 is 6. -6 plus 6 is 0. As we expected, remainder is 0. We know that it should be 0 because with the remainder theorem we got remainder 0. Now look at these coefficients. By looking at these coefficients, we know that the quotient of dividing that polynomial by x plus 1 is x to the 2 plus x minus 6. So now we know that x to the 3 plus 2x to the 2 minus 5x minus 6 is x plus 1, this factor, times by this, x to the 2 plus x minus 6. The second bracket here is a simple quadratic expression. And when we get to a quadratic equation or quadratic expression, we don't need to use this method again because factoring a quadratic expression is very simple. Now for factoring this x to the 2 plus x minus 6, we are looking for two numbers that their product is -6 and their sum is 1. And those numbers are, so we have x plus 1 times by x plus 3 times x minus 2. 3 times -2 is -6. 3 minus 2 is 1. Now we have the fully factored form of this given polynomial here. If you like to see more examples about factoring polynomials, watch my video dedicated for this topic. I have a full video with lots of examples for factoring polynomials. If you want to learn this method fully and understand different type of questions, please watch that video. Let's continue to the next topic, which is graphing polynomial functions. Any polynomial functions is odd degree or even degree. If it is odd degree, the two ends of the polynomial are going in opposite direction. Odd degree, opposite direction. If the leading coefficient, a is the leading coefficient here. If the leading coefficient of the polynomial is positive, the left end is going to -infinity in the third quadrant, and the right end is going to +infinity in the first quadrant. So any polynomial of odd degree, degree 3, 5, and so on, if the leading coefficient is positive, is the end behavior is like this. The left end down, the right end up. The behavior between these two ends can be different depending to the question. It can go up and down several times. But we are talking about the end behavior of the polynomial functions based on odd degree or even degree. So odd degree, opposite direction. But if the leading coefficient is negative, the two ends are again opposite direction, but the left end is going up, the right end is going down. The left end is in quadrant 2, the right end is in quadrant 4. And again, between these two ends, it can go up and down several times. You can imagine what happens here. It crosses x-axis depending to the degree of polynomial many times. Now let's focus on the even degree. In the even degree, the two ends are in the same direction. They go up or both go down. If the leading coefficient is positive, they go up. So when the leading coefficient is positive, the two ends are going up. When the leading coefficient is negative, the two ends are going down. And again, between these two ends, it can go up and down and maybe cross x-axis. It depends to the particular question that we are solving. Now that we have learned about the end behavior of a polynomial function in the graph of the function of polynomials, let us start doing some examples. As the first example, we want to graph the function x minus 2 times x plus 1 times x plus 3. The most important thing in graphing of any polynomial function is the degree of that polynomial. This given polynomial here is degree 3. How we know it's of degree 3? Look at these brackets. We have 3 brackets. This bracket has x to the 1. So this is degree 1, this is degree 1, and this is degree 1. If you multiply 3x of degree 1 by each other, it would be degree 3. X times x times x is x to the 3. So this polynomial is of degree 3. This is the first thing that always you have to find. After we figure out the degree of the polynomial, we look at the leading coefficient. And in these brackets, we don't have any negative for x. So x times x times x would be x to the 3 positive. And because this coefficient here is 1, so the coefficient or leading coefficient is positive. The sign of the leading coefficient is very important. As we saw above, leading coefficient is positive. Remember, the leading coefficient is very important because it changes the behavior, the end behavior of the function. The other thing that can be helpful for graphing polynomial function is finding the x-intercepts. When the polynomial is in the factored form, finding the x-intercepts is very easy. We have to set the polynomial, the equation of the given polynomial, equal to 0. And easily we can find the x-intercepts. These brackets multiplied by each other, it equals 0. So by setting each of these brackets individually equal to 0, we can find the x-intercept. From here, x is 2. From here, x is negative 1. And from this bracket, x is negative 3. Now we have the x-intercepts, the degree of the polynomial, and we know the leading coefficient is positive. Everything is ready to graph the function. Let me draw axes here. The x-intercepts are negative 1, negative 3, and 2. So, negative 1, negative 2, negative 3, negative 4, 1, 2, 3, 4 here. The x-intercepts are negative 3 and negative 1 and 2. So we know that our polynomial passes through these points. This polynomial is of degree 3, and if you remember, as we discussed before, when the degree of polynomial is odd, the ends are going, the end of the polynomial, the graph of the polynomial are going opposite direction. When the leading coefficient is positive, the right end is going up, the left end is going down in the third quadrant. So we know that, as we discussed before, that the right end is going up this way, the left end is going down here. And now we know that we have to start from here, passing through these points, and we can graph the function easily. Now you know that the graph of our function should be something like this. The left end is going down in the third quadrant to the negative infinity. The right end in the first quadrant going to positive infinity. This is the graph of this polynomial function. Let's do another example. Here we want to sketch the graph of negative x times x minus 2 times x plus 2 times x minus 4. Immediately we have to figure out the degree of the polynomial. This polynomial is of degree 4. Leading coefficient, as you can see here, is negative. Leading coefficient is negative. What are the x-intercepts? If we set this equation equal to 0, let me do it here, negative x times x minus 2 times x plus 2 times x minus 5 equal to 0. We are going to have, basically in this case, 4 zeros. If we set this negative x equal to 0, we are going to get x equals 0. From this, x equals 2. From here, x is negative 2. And from this, x equals 5. Everything that we need is ready here, so we can start graphing the polynomial. We draw x-axis and y-axis. The leading coefficient is negative, the degree is 4. When the degree is even, the two ends are going same direction. But because leading coefficient is negative, we know that the left end and right end are going down in the third and fourth quadrant. The zeros are 0, 1 root is here, 2, 1, 2, 2 is here, 5, 3, 4, 5, let me erase these ends here, 5 is here, and the other root is negative 2, negative 1, negative 2. So we know that our graph should pass through these points. The left end is going down, the right end is going down, and now we can graph our function simply by passing through these points. And this is the graph of this function. Now look at this example. X minus 2 times x plus 3 times x minus 1 to the 2. First, tell me what is the degree of this polynomial. This polynomial is of degree 4. The reason is that we have x minus 2 of degree 1, and degree 2. Attention, x minus 1 to the 2, it means that x minus 1 times x minus 1. So basically this is of multiplicity 2. This factor is repeated. So it is of multiplicity 2 because it's repeated twice. So this is 2 plus 1 plus 1, 4. This is degree 4. Leading coefficient is positive or negative. As you can see here, leading coefficient is 1 and it is positive. So leading coefficient is positive. Degree 4, it means that it's even degree, so the two ends are going same direction. Odd degree, opposite direction. Same degree, even degree, same direction. So the two ends are going up because the leading coefficient is positive. The only thing that we need to find before graphing the function are the zeros or the roots or x-intercepts. Zeros, roots, x-intercepts. All of these are same thing, same numbers. What are the zeros? If we set this equation x minus 2 times x plus 3 times x minus 1 to the 2 equals 0, we are going to have 2, negative 3, and 1 as the roots. Attention, these are simple roots, but this root is a root that comes from this factor, but this is x minus 1 times x minus 1 because it is raised to the 2. So this root is of multiplicity of 2. And when the multiplicity is 2 or 4 or 6, it's even, it has to be graphed a little in a different way, which I will show you in a moment. So we have a polynomial of degree 4, leading coefficient is positive, and these are the roots. Let's graph x-axis and y-axis. The roots are 1 root is here, 2, 3, 4, 5, and so on. The other root is 2 is here, and we have one root at negative 3, negative 1, negative 2, and negative 3 somewhere here. This point. Before I graph this function, let me mention something here. If you are finding the graphing of polynomial functions easy, please pay attention that these polynomials here are in the factored form. It's given to us in the factored form. If a polynomial is not in the factored form, first we have to factor them, which takes some time. Then we can graph them with this method. So first of all, we have to factor each polynomial. Then after factoring the polynomial, we can graph it. The degree is even, leading coefficient is positive, so the two ends are going up. So I know that I have a graph that the two ends, left end and right end, are going up. Don't forget this. -3 and 2 are simple roots, simple zeros, simple x-intercepts. So as usual, we know that we have one left end here, so we pass through -3. Then when we get to 1, we know that it's of multiplicity 2. When you have a root that is of multiplicity 2, please pay attention. You should not simply pass through that point like a simple root. When you have a root that is of multiplicity 2, 4, 6, any multiplicity, even multiplicity, when you get close to that point, you should bounce at that point. The graph bounces at that point. Remember graph of y equals x to the 2. The graph of y x to the 2 is like this. The 0 is here. When you get close to 0, what happens? You bounce. You are not going through the 0. The reason that you have to bounce is similar to the reason that when we graph x to the 2, we bounce at 0. So here, we pass through -3. But when we get close to 1, I know that I have to bounce. So I'm not going directly through this root. I know that I have to bounce. So I go through this point. Before getting to -1, I know that I have to bounce. So I'm going this way. But I know that I have another x-intercept, which is 2. So I know that I should not continue going down. I have to pass through this point. And I know that on top of that, the leading coefficient is positive, so the right end should go up. So we go a little down, then we go up again. We know that we have to back because we have to pass through 2. And we know that the right end should be up. And this is the graph of this function here. So whenever we have a root that is not a simple root, it's of multiplicity 2, 4, 6 and so on, we have to bounce at that x-intercept or root or 0. Sketch the function y equals -x minus 1 times x plus 2 to the 2 times x minus 3 to the 3. What is the degree of this polynomial? Immediately by looking at this polynomial, we know that it is of degree 6. 3 plus 2 plus 1 is 6. So this is of degree 6. Leading coefficient of this polynomial is positive or negative. Leading coefficient is negative. Degree is even. So the two ends are going same direction, but leading coefficient is negative. So immediately we know that the two ends are going down. But before graphing the function, we have to find the x-intercepts or zeros of the function. By setting the polynomial equal to 0, we can find the x-intercepts. X minus 1 times x plus 2 to the 2 times x minus 3 to the 3 equal to 0. We are going to have 1, -2 and 3 as the roots. From this we get 1, from the other one we get -2, and from the last one we are going to get 3. Now that we have the roots, we are ready to graph the given function. 1 is here, 2, 3. So one root is here, one root is here. Negative 2, negative 1, negative 2, one root is here at negative 2. And don't forget, we know that the two ends are going downwards. So the graph of this function, let's start from the left side for graphing. When we get close to negative 2, should I simply go to this point, or I should bounce, or any idea here? Attention, negative 2 is of multiplicity 2. Whenever you are writing a root, if it's not simple, mention. Look at here, x plus 2 to the 2. So it is of multiplicity of 2. So this is not a simple root. So we are not simply going to this point. We have to bounce here. So when I start graphing the function, I know that when I get close to this point, I have to bounce. So we start from down here, we go to this point and we bounce. Now, what about 1? 1 is a simple root, so simply we go to 1. What about 3? 3 is not a simple root, but its multiplicity is 3. And it is the first time that we see such a situation that its multiplicity is 3. What happens when we have a multiplicity? Should we bounce or not? No, we are not going to bounce, but graphing to a point that its multiplicity is not 1, is not a simple root, is a little different. Let me explain this to you here. For that, you need to remember graph of y equals x to the 3 or x to the 5. The graph of x to the 3 and x to the 5 and x to the 7 through the 0 is like this. Look at this point. When we have functions with odd degree at this 0, we are not simply going through this point. We get close to this point like a bounce, but we are not bouncing. Basically, we go through, but it's like a flat curve here. So, to graph our function, we simply pass through 1, but we know that when we want to go through point 3, we should graph something like x cubed, x to the 3. So let me show you what you have to do here. You continue a little going up, then when you get close to 3, your graph should be a little flat here, and then you continue going down. Let me make this a little better. So we go up, then we get close to this point, and then we continue going down. Something like this. Something like this. Let me try again. This is not what I expected to graph. We get close to this point, we get a little flat, and then we go down. Here we want to do the opposite of the above questions. Here we are given a graph. From the given graph, we want to write a possible equation for this graph. So we want to find an equation for this given graph. And we have supposed that this is a graph of a polynomial function. First of all, by looking at the end behavior of this given function, immediately we can figure out that this polynomial is of degree odd. And probably it should be of degree 3 because it has 3 roots or 3 zeros or 3 x-intercepts, as you can see here. So we know that because how we know it's odd degree? Because the end by looking at the end behavior of the graph, one end is going up, the other going down, opposite direction, odd degree. So we know that this polynomial is of odd degree. But what is the equation? Because we know that the roots are -4, -1, and 3. And as you can see, the graph is simply passed through these points. No bounce has happened, or we don't have anything like this or like this when it crosses the x-axis. So we know that these are simple roots. So this polynomial function has 3 roots and those roots are simple. So we know that one of the factor is x plus 4 corresponding to this. If we set this equal to 0, x would be negative 4, this point. The other factor is x plus 1 and the final factor is x minus 3. We have 3 brackets is of degree 3, odd degree, as we expected. But attention, we are given one extra information here. We are given the coordinate of this point here, the y-intercept. And because of that, we can find the coefficient, the value of the leading coefficient a. So always we consider one value a outside of these brackets. That value can be any number. We can figure out that value only if we have one point other than the x-intercepts. We use the x-intercepts only to figure out the factors. But for finding the leading coefficient, we need to know the coordinate of one extra point on the given graph. It's not necessarily the y-intercept. In this case, it's y-intercept. But it can be the coordinate of, for example, this point. For example, they can tell you this point is 4, 7. Or any number. So, we need to know the coordinate of one extra point. Otherwise, we cannot figure out that value. We can suppose it's 1 or 2. Because it's not given any other information, it can be any value. But here we can find the value of a. How? Now we know that our function crosses the y-axis at -1. Which means that if we plug in 0 for x here, because that point is, what is coordinate of this point here? 0, -9. The x is 0, y is negative. So if we plug in 0 in this function, so if we plug in 0 in this equation, the y value should be 9, -9. Then we have a times 0 plus 4 is 4, 0 plus 1 is 1, 0 minus 3 is -3. We plug in 0 for x and this should equal to -9. From here, -3 times 1 times 4 is -12a equals -9. So a is 9 over 12 or 3 over 4. As we expected, we got a positive value for the leading coefficient, which makes sense because the left end is going down, the right end is going up, the leading coefficient should be positive. If this was negative, then it couldn't be this graph, because when this is negative and it's odd degree, then the left end is going up, the right end is going down. So this answer is right, and it confirms that this value of a is for this graph. Let's do another example. Here we are given again a function, but it has only 2 x-intercepts, -4 and 5, and by looking at the given graph, we can guess that probably this one is also of degree 3, because left end is down, right end is up, and it crosses x-axis at 2 points, so it should be degree 3. Why it's not of degree 2? Because attention, if it was degree 2 or 4 or 6, then the 2 ends are going same direction, but here the 2 ends are going opposite direction, one end down, the other end up. So definitely this is odd degree. Immediately we say y equals a times x plus 4 times x minus 5 to the 2. Based on the roots, we know that the equation should be like this. Why we put power 2 for x minus 5? Because from the graph we can see that we have a bounce at 5. So it should be x minus 5 to an even power. Maybe you wonder why you put 2 here, why it's not 4. It can be 4. It can be 6. We don't know. That's the reason in the questions like this, they tell you write a possible equation for the given graph. It means that there are other possibilities, because we can put power 4 here, power 6. But usually we prefer to write with the least possible degree. That's the reason we consider 2 for the power of x minus 5. For finding a, again we have this point here, this point. So we expect that if we plug in 0 for x, the y be equal to 50. If we plug in 0 for x, then we have a times 0 plus 4 times 0 minus 5 to the 2, it should equal to 50. Negative 5 to the 2 is 25 times 4 is 100, 100a is 50. So we have 100a equals 50, so a is 50 over 100 or 1/2. So the equation for this given graph is 1/2 times x plus 4 x minus 5 to the 2. I hope by watching this video you have learned about polynomials, graphing polynomials, characteristics of polynomials, how they behave, what are the roots, how to factor polynomials, and other things. If you want to learn more about polynomials and you want to see more examples about polynomials, for each of these topics that we discussed in this video, I have a separate video with many examples. Please watch those videos to learn these topics fully. If you like this video, please subscribe in my channel and see you in the next videos.